This lecture is on historical simulation and extreme value theory. Let me start with an outline of today's lecture. There are three main topics for today. First topic is historical simulation. What we will do there, we will look to a portfolio of assets that we observe today. And the question is, could we make use of the historical observations of each of these assets in the portfolio to get an idea, to get an impression of what the portfolio may do in 1 year from now or in 1 day from now. So we use past realized returns to make a probability assessment of 1 day or 1 month or 1 year out of sample. That's the first element. We will look to the most basic approach there, and we have two more generalized extensions to the historical simulation approach. Then we will talk about the accuracy of value at risk. Well, value at risk is calculated based on observations. Then we estimate a probability distribution function, and we look to a percentile of that probability distribution function. But these parameters are estimated with uncertainty, which is usually reflected with a standard error, for example. And the question is, could we, when we provide an estimate for the value at risk, could we also give a level of accuracy that comes with the value at risk? And we will give an example for that. And then the third topic for today deals with extreme value theory. We already briefly discussed that in an earlier lecture where we talked about the power law. Extreme value theory is relevant when we are interested in observations with very low probability of occurrence. We also would say that's observations which occur very far in the tail of the distribution function. Think, for example, of extreme losses that could occur. Very often you don't observe these extreme losses, but you want to extrapolate from the distribution function. And extreme value theory is a very valuable tool to do that. So we will discuss that as a third topic for today. Historical simulation. Well, what is historical simulation? Look to a portfolio of assets. To begin with, look to a single asset. And for this asset, you observe its price today. But you also observe, or you also have access to the realized returns and the realized observations in the past of this asset. And what you very simply could do, you could say, well, I believe that, that the asset return, as it will apply for the next period, so from today, for example, to tomorrow, that that distribution function should be the same as it was in the past. So then we say that the asset returns are homogeneous over time and that they have the same probability distribution function. If that's the case, then the realized returns that we have observed historically are then also a good indicator or good representation for the distribution function of that asset return. And what we will do is we will simply use these observations, these realized observations, as the possible outcomes applying to the current asset value for the next period. And then in a way, we simulate, based on historical information, we simulate a distribution function for the future. So that's also why we call it, I'm sorry. That's also why we call it historical simulation. You could generalize this principle of historical simulation and not only look to a single asset. So for a single asset, we just said, well, we observe the price of the asset today and we observe its returns and its prices historically. And then we use these historically observed asset returns as a distribution function for 1 day or 1 week or 1 month out of sample. If we look to a portfolio of multiple assets, then of course for each asset we could do that. For each asset in the portfolio, we observe today's value. And we also have at our disposal the historical price observations for all these assets. So we also then can calculate the historical returns for all these assets. What's interesting about that is that what we then observe is not only the possible changes, the possible returns on each asset individually, but because we observe simultaneously how other assets or how assets historically have co-moved, we then implicitly have incorporated also in the distribution function, in the multivariate distribution function, the co-movements of all the possible assets. And that's very interesting. In earlier chapters, we talked about standard deviations and correlation, for example, or copulas to measure uncertainty and co-movement. Well, with historical simulation in a portfolio context, where we look to the past co-movements that we have observed for assets in the portfolio, and then subsequently we will apply these past observed returns with their co-movements out of sample to represent the portfolio distribution function out of sample. We have taken all complex co-movements that were in the data. We have incorporated them in the distribution function to apply out of sample. And that's very powerful, of course. The assumption that you make, that's the flip side of this story, is that you believe that the returns that you have observed historically are representative for the future. So that there's homogeneity over time, and that also the co-movement between the asset returns that you have observed historically also are representative for the future. Again, homogeneity and co-movement. And we will come to say two extensions of this basic model to perhaps better deal with these assumptions. For now, let's assume that we observe T+1 historically realized prices, and we observe them at time 0, time 1, time 2 until time capital T. Time capital T is the last period that we observe an asset price or the asset price of the portfolio. So if we are today, then we are today at time capital T, and the historical price observations were at time t-1, which is yesterday, time t-2, which is the day before yesterday, until time 0, which is capital T days ago. And from these T+1 prices, we can calculate returns. So the first return that we calculate is from time 0 to time 1, and we call that return 1. So you always refer to the latest time point in the period where you calculate the return. So that means with capital T+1 realized prices, I can calculate capital T returns, and we call these returns R1, R2, R3 until R capital T. Also important is that, well, we are going to use these historically observed returns as possible returns to apply from time capital T, which is today, to time capital T+1, which is, for example, tomorrow. And then if we're going to look out sample, say as of time capital T to time capital T+1, then we talk about a probability distribution function, because all these historically observed returns, which at that time are realizations, they become possible scenarios out of sample, which also means that they each have a probability. In this basic case, this first case that we discussed, all the realized observations, all the realized returns have equal probability of occurrence. Given that there are capital T returns that we have calculated based on the historical prices, the probability of each of these scenario returns is 1 over capital T. Let's see if we can also then reflect this in mathematical notation. I begin with the introduction of the price of an asset. The price of asset J at time I denote that with VJI. And then the time periods where we observe these prices. So the historical time periods, it starts at time 0, then time 1 until time capital T. We assume that the portfolio consists of multiple assets, and these assets are denoted with the subscript J, and then J runs from 1 until capital N. So there are capital N assets, and the prices of these assets, they are historically, of course, all known, but the last moment that they are known, which is today, is the moment time capital T. So we have today at our disposal the asset values of all the assets in the portfolios, which for asset 1 today is denoted with V1T, and for asset 2 it's denoted with V2T, and with the last asset in the portfolio, its value today is VNT. And then what we want to do is we want to first calculate the value of the portfolio today, which is simply the sum of V1T plus V2T and so on until VNT. But then given that we have the portfolio value today, we are interested to know, well, what could be a possible value for the portfolio in the next time period, so at time t plus 1. So I'm going to represent that distribution function with different scenarios. And the ith possible portfolio value at time t plus 1, so one period from today, is denoted with pi t plus 1 I. So the pi reflects, then the capital pi reflects the portfolio value. T plus 1 means we are going to look 1 day out of sample, and the I reflects, say that this is just the ith possible portfolio value that could occur. Well, how am I going to calculate this scenario? I'm going to look to the asset value today. Well, to begin with, the asset value of asset 1, V1T, because that capital T is today, and I multiply that with the return that I've observed, 1 plus the return that I've observed historically for asset 1. And well, that is then V1I divided by V1I minus 1. That's exactly the increment, 1 plus the increment of the asset value at time from time I minus 1 to time I. So that's 1 plus the return of the asset. And I multiply that historically observed return with the asset value of asset 1 today. I do the same for asset 2, asset 3, and so on. Then I get to the last asset, and its value at time t today is VNT. And also for VNT, I need to look, well, what is a possible development of that asset value? And then I'm going to look historically again to, well, what was the development of the asset N from time I minus 1 until time I, which is then really just 1 plus the historically observed return for period I of asset N, and that's then the fraction of the two. So what I've done, I've looked to the observed prices of the assets, each asset at the latest moment available at time capital T, and I multiply each of these assets with the historically observed return, 1 plus the historically observed return for each asset. And the nice thing, of course, is that co-movements are incorporated in here, because if I multiply asset 1 with the realized return at time I, then I also do the same thing for asset N. I multiply it with the realized return for asset N, but then also at time I. So then we see that the co-movements are incorporated through the returns. Once I've then determined a possible realization, a possible scenario for the portfolio value at time t plus 1, I could easily calculate the return that comes with that portfolio value, because I look then to the realized portfolio value pi t plus 1I, and I divide it by today's value of the portfolio, which is the sum of all the assets at time capital T, and I subtract 1. So in that case, if I have capital T historically observed returns, I could create capital T possible future portfolio values and portfolio returns, and that gives me a distribution function for the possible outcomes at time t plus 1 for the portfolio. And once more, the nice thing is that it then includes possible shifts, possible deviations for each asset individually, but it also includes co-movements of these assets in the portfolio. Well, if you have these capital T possible realizations of the portfolio returns, then what you could do next is you could simply sort them from the lowest to the highest. So the lowest return, the most negative return, is then the worst event that happens in your distribution function. And of course, we are interested in that left tail where the negative returns occur. So we have possible realizations for the returns, which gives you then the distribution function. And we also know that because all these returns have been calculated based on historical observations, and there were capital T historical observations, in this case, we assume that they all have equal likeliness of occurrence. So each return, each portfolio return that we have generated like this has a probability of occurrence of 1 over capital T. So then once you have sorted the returns, next what you do is you determine the cumulative distribution function that comes with it, and then to arrive at the value at risk, you simply look where the cumulative normal distribution function, where the cumulative probability distribution function is equal to the confidence level of the value at risk. So what's the probability mass in the left tail? And once that's equal to that cumulative probability, then you are at the value at risk. So that's an easy way of doing it. And second, if you want then also to determine the expected shortfall, then you look to all the returns that are worse than the value at risk return, and you simply take the average of these returns. So let's see how that works out in an example. I constructed a portfolio which has a value of $1 million at the 4th of December 2019. And these $1 million are for 40% invested in the Dow Jones Industrial Average, for 20% in the CAC 40, for 30% in the FTSE 100, and for 10% in the Nikkei 225. And because these are indices which apply to different countries and have then different currencies, I first made sure that all the assets in this portfolio are dollar hedged, which means that their values are always expressed in dollars, so that we don't have anything to do with currency risk here. So I've taken 501 historical observations. So the last observation is on the 4th of December, and then I work backwards to have 501 days with possible values for these 4 indices to represent the assets in the portfolio. So which means that I can then also calculate 1 plus the returns of each asset in the portfolio. 1 plus RJI is simply the return for asset J at time I historically, which you calculate then as the value of the index J at time I divided by the value of index J at time I minus 1. So very similar to the formula that you saw earlier. I move from prices to returns, which means that of the 501 price observations, I calculate 500 returns, which means that the probability of each return that I'm going to determine is 1 over 500, it's 0.2% probability. And then once I've done all the calculations and I've represented the probability distribution function for 1 day out of sample, so I move then from the 4th of December to the 5th of December, and the 5th of December is still uncertain. I want to have a probability distribution function for that. Then once I have that probability distribution function, I also want to know, well, what is the value at risk and what is the expected shortfall that could occur if I am at 4th December and I look to 5th of December. And the critical values, so the probability mass in the tail of the distribution, the left tail of the distribution function, I will set to 5%. And the reason why I set it to 5% is because I have limited number of observations and I still want to show something on the slides. But obviously you could also set it to 1%, but then the number of observations becomes very low. So here is a presentation of 25 observations of the 501 observations that were historically retrieved. So we indicate them with 0, 1, 2, 3 until 25. These are the price observations. So this is a price observation on the 18th of April 2017, the 19th of April 2017, the 20th of April 2017, and so on. And then you see the price developments for the Dow Jones Industrial Average, the CAC 40, FTSE 100, Nikkei 225. And these price developments help us to, which are on the left table, help us to then determine returns, 1+ returns in the right table. So the Dow Jones Industrial Average has a realized return on the 19th of April of 0.994, which is the result of dividing 204 by 205. The CAC 40 has a 1+ return realization on the 19th of April of 1.004, which is simply the calculation of 5361 divided by 5339, and so on. So in this case, for 500 returns, well, in this case for the 501 prices, from the 501 prices, I have determined 500 returns for all the four assets in the portfolio. Then, if I'm going to apply these portfolio values, these possible 1+ returns to the portfolio value as it applied at time T, then the 0 line shows the initial value of the portfolio as it was invested. 40% in the Dow Jones Industrial Average, so that's 400,000. 20% in the CAC 40, which is $200,000. Then 30% in the FTSE 100, which is 300,000, and 10% in the Nikkei 225, which is 100,000. So these are the initial values of my portfolio assets. And if I add these assets up, I get the total portfolio value, which is 1 million. Then the numbers 1 to 25 give me the 25 possible historical realizations that I've seen, and then applied every time to this portfolio that you see in line 0. So to the 400,000, 200,000, 300,000, and 100,000. So I look to the 1+ realized return of the Dow Jones Industrial Average at time 1 historically, and I apply to the 400,000. And so here we see that then the value of the Dow Jones Industrial Average portfolio goes to 397,681 as a value. For the CAC 40 it goes to 280.40, and for the FTSE 100 it goes to 299,687, and so on. And then if I add up all these portfolio values in this first scenario, in scenario 1, then the portfolio will get a value of 998.012. Which means that if I look to this realization in terms of portfolio return, the portfolio had a value of 1 million at time T, and in this first scenario for time T plus 1, its value is lower and the portfolio return is minus 20 basis points. Then line 2 again looks to historically realized returns for the assets in the portfolio, applied again to line 0, applied again to the portfolio values at time T. And then in this case, the portfolio in the end grows. It grows to a value of 1,008,000 and something, which is a realized portfolio return of 81 basis points. And here in this representation, you see it for 25 historically observed returns, but actually I do it for 500 observed returns. So that means that from time T, which is today, to time T plus 1, I have 500 possible outcomes in terms of returns of what could occur to my portfolio. So that's the left side of the table. So I have not displayed everything, but only 25 possible returns, or 25 possible returns from the 500 returns that I've generated. Simply doesn't fit on the slide. Then in the right table, what I've done, I've taken all the historically generated portfolio returns. So that's the last column of the left table. But then I took all 500 of them and I sorted them from low to high. And then you see that the worst return that was observed historically for one day was minus 3.05%. Then the second worst was minus 2.43%, and so on. So I've sorted them, and with them I've also added the probability of occurrence. What we said is, well, each historically observed return is equally likely to occur, so they all have probability of 0.2%. Then to determine the cumulative probability, I simply need to add up the probabilities which are more left in the tail. So the worst case of minus 3.04% has a cumulative probability of 0.2%, but then the second worst has a cumulative probability of 0.4 and then 0.6, 0.8. So every time I add the probability of the individual return occurring. So if I do that, then after 25 observations of these sorted realized returns, I arrive at a cumulative probability level of 5%. And we said, well, we would like to determine the value at risk and the expected shortfall associated with a left tail of returns that is consistent with a probability mass of 5%. So that means that the 25th worst realization that I've seen from my portfolio return, which in this case is minus 1.2%, is then also the value at risk return that applies with a 5% probability mass. So it's very easy to determine the value at risk. Simply you sort the returns from lowest to highest, and then you take the 25th first worst return, because that's consistent with a probability mass of 5%. So that's how you determine value at risk. The expected shortfall is also easily determined. All the probabilities are equal for the returns which are worse than the value at risk, which means that I can simply take the average of all the returns that have occurred in the tail and which are worse than the value at risk, which is then the average of the returns in line 1 until line 24, which gives a value of minus 1.68%. So very easy way to determine well, first of all, to do the historical simulation, to generate a probability distribution function for next day's possible returns on your portfolio, including all sorts of co-movements and deviations that we've seen in the past. And then a very easy principle how you arrive at value at risk and expected shortfall, simply by sorting the portfolio returns, take the value at risk, which has the 25th worst value, and then for the expected shortfall, take the average of the 24 returns which are even worse than the value at risk. So this is the first basic case. There may be a good reason to say, well, do I believe that all these 500 or 501 historical prices that are observed for the assets, and then the 500 associated returns that come with that, whether they are equally representative for the distribution function that applies from today to tomorrow? And it seems like very natural to say that returns that have occurred further in the past are further away from today and maybe less representative for today's situation. And that's what we will address in this first extension to the historical simulation approach that you just saw. What we will do is we will generate exactly the same returns and exactly the same portfolio returns that you saw in the previous case, so nothing changes there. But in the previous case, we attached equal probability, equal weight, and also equal probability to all of these historically observed portfolio returns. What we will do in this first extension, we will say a return which is more recent is more important, should get more weight, and then afterwards also in the probability distribution function will get a higher probability of occurrence. And the way that we represent these weights, and also then afterwards the interpretation of these weights as probabilities, is that we use an exponentially weighted moving average scheme to determine the weights. We put lambda to 0.94, and we say, well, the weight that we attach to an observation that occurs at time I, so I is a time in the past, and time capital T is today, then we say, well, we will take the power we take lambda to the power time today minus time in the past. And the higher than this I, the more recent I am in to today. So that means that the power is then lower, and it means that the weight will be higher. So if I'm very far away, so if I'm at time 1 or time 2, then the power that I use for lambda is higher, which means that if I take a number smaller than 1 to a high power, then the weight will become lower. So this is a smooth way to attach weights and then also probabilities to historical observations. These weights, if you represent them with the formula like this, they nicely add up to 1 if we add them up, which means that then they also very easily have the probability interpretation, and it's simply then the probability interpretation for a return from time t to time t plus 1, so 1 period out of sample. So here I show a table with 3 subsets. The first part of the table shows the 10 observations or 11 observations from time 0 to time 1, which are furthest away from today. Today is time 500, so time 0, 1, 2, 3, and 10, they are 500 to 490 days away from today. So you see simply the values of the portfolios at that time, and you see the weight that we attach, the exponentially weighted moving average weights, which say with 2 decimal points are not distinguishable from 0. It says 0.00%. So the returns are exactly the same as they were before, but the weight now is different. I also took some observations 100 days ago until 90 days ago, which is the middle part. The returns that are calculated are exactly calculated as in the previous case. And then you see that the weights at least become a little bit higher, 0.01% until 0.02%, something like that. And then if I look to the most recent weights, so for the observations from time 490 until today, time 500, there you see that the weights are much higher, 3.2%, 4.1%, and so on, and the most recent return 6%. So what happens is that we still have the same returns as possible outcomes for my portfolio return, or for the assets in my portfolio, which means that I can calculate the same portfolio returns that could occur. Only what changes now is that the probability of occurrence of these portfolio returns are different. And why does that have an impact? So if I'm going to sort now again the portfolio returns from low to high, I get exactly the same portfolio returns that I had before, but now the associated probability that comes with each portfolio return is different. So in the previous case, it was always 0.2% because we assumed that each return was equally likely to happen. So here we explicitly reflect the distance of the return occurrence from today. And then you see that in order to get to a cumulative probability of 5%, I do not need 25 historically sorted returns, but I need more. In this case, it's 50. And that's simply the case because a lot of the very negative returns that have occurred historically have occurred in a time period which was relatively far away from today. So that means that it gets low probability. So you see, for example, the worst one gets a probability of 0.00%. So there is some probability mass, but it's not reflected with 2 decimals behind the comma. And then there is only one return, return 19, which is minus 1.41% for the portfolio, which has occurred more recently because there we see that the probability of occurrence is 2.37%. So it reflects then clearly what we wanted to have, that more recent return observations get more weight, which means that before I arrive at the most serious, well, at the value at risk probability of 5%, I am with scenario, well, with the 50th worst return, which is minus 0.97%. Because there the probability say increases for the first time the 5% level. So that means if I believe that this is true, that the more recent observations are better representative for the probability distribution function from today to tomorrow, I can attach different weights. So then I arrive also in this case at a lower value at risk statement than before. So that's the first thing. So I take the 50th return, portfolio return that was realized because the probability mass there, see, for the first time exceeds the critical value. So then the second calculation is the calculation of the expected shortfall. So again, what I do is I look to all the returns which are even worse than the value at risk return. So that's 49 possible returns that could occur. But these returns now do not have equally likely probability of occurrence, but some probabilities are lower and others are higher. So what I will do next, in order to reflect that, I will take the weighted average of these negative returns, which are even worse than the value at risk. So that means that I will probability weight the returns. So I will multiply each return with its probability, and I will then sum them up, and I will divide this sum of the weighted returns, probability weighted returns, I will divide it by the sum of all the probability. Then indeed the returns, these negative returns, the returns in the tail are probability weighted, which is exactly the definition of the expected shortfall. If I do that, I arrive at an expected shortfall of minus 1.22%. Then the second possible extension of the historical simulation approach is the basics historical simulation approach that we began this lecture with, is to say, well, it's not the distance to today that is important, but it's in fact the volatility regime that the observation is in. Basically what I'm saying is, well, let's look to the volatility regime that I am in today. And if I look in the past to a particular return, then this return maybe has occurred in a different volatility regime. Maybe the volatility regime was lower, it was an easier period, or the volatility regime was higher, it was more turbulence. And then what we say is, well, what we want to do is we want to define a factor to look to the return that happened in a past volatility regime and then make it representative for the volatility regime that you are in today. And the way that we do that is, first of all, we need to determine a way to represent the volatility regime. And very soon we will use the exponentially weighted moving average volatility updating to do that. But in terms of definition, I need to know the volatility regime as it applies today. So that is then associated with the return that would happen from today to tomorrow for each asset. And for asset J, then it's the volatility, the sigma of asset J associated with the return from time t to time t plus 1. So that's the volatility regime that I'm exposed to today. So historically, when I observe the returns, then there's also a volatility regime, and that volatility regime for asset J for an historical observed return over period I is denoted with sigma Ji. Now, at the bottom, I'm again going to look to the portfolio development, the portfolio value development from time t to time t plus 1. So here you see the possible portfolio value at time t plus 1. The pi reflects the value of the portfolio. T plus 1 is 1 day from today, so 1 day out of sample. And the I says, well, this is the ith possible scenario that could occur. I look to each asset individually, so I look to V1t, V2t until Vnt. So V1t is the value of the asset 1 today at time capital T. And I'm going to multiply that with 1 plus the possible return, historical asset return, but I want to adjust that historical asset return. So V1i minus V1i minus 1 divided by V1i minus 1, that's exactly the discrete return that occurred for asset 1 for period I. So that's a return that we observed historically, and we said, well, this return occurred historically in a volatility regime, and that volatility regime is reflected with sigma 1i, the volatility of asset 1 also at period I. So what I will do is I will divide that historically observed return by its volatility regime, so then I standardize it, and I multiply it with the volatility regime as it applies today, from time t to time t plus 1. So that's the sigma 1t plus 1. So I'm simply then inflating or deflating historically observed returns, and I do that exactly by looking to the fraction of the volatility regime today over the volatility regime when I observe that historically observed return. I do that for asset 1, for asset 2, and on the right hand side you also see it for asset n. Well, so then we need a volatility updating scheme for each asset return volatility. So we will use exponentially weighted moving average for that, set lambda equal to 0.94. And also a slight detail as well, this volatility regime, this volatility updating principle needs a starting value. And for the starting value, we take the unconditional variance over all the historical returns that we have seen. So that's the first thing. The second thing is that in this case, all the observations that we are going to determine like this. So we observe an historically observed return. We're going to inflate it or deflate it to make it representative for the volatility regime that we are on today. Each return that arises in such a way has equally a probability of occurrence, given that we have capital T historically observed returns. Each return will have a probability of 1 over capital T. So let's see how that works if we are going to do that. So I displayed here only 10 observations, 10 prices of the 501 prices that are available. So in the left table, there are simply the prices of all the assets. Then the table next, you determine the asset returns. Because I need these asset returns, I need to determine the average and the standard deviation for it, because it's for these asset returns that I'm going to do the volatility updating. So the volatility is related to the asset returns, so the historically asset returns. And in that volatility updating scheme, there is 2 elements that I need. I need the volatility of the previous time period, the previous day. And I will start then that with the variance of all the historically observed returns. So you see that there is a standard deviation reported for each asset on the top of the second table. If I square that, then I have my starting value for the volatility updating scheme for each asset. And I need a shock. I need which we have indicated with the U, and that shock is simply the return that I've determined in table 2, and I subtract the mean from it. Usually the mean can be ignored, but for completeness sake, I've added it. You see that it's very small, the average there, but still then it's complete. So that delivers me a U, a Nu's factor. Lambda was set to 0.94. And then I can do my volatility updating scheme. So I start the returns with a starting value, which is the squared of the standard deviations that I've determined in table 2. And then I use the formula at the top right, where the volatility for asset J at day I is determined as 0.94 times the variance in the previous time period for that asset, plus 1 minus the lambda times the shock that I've determined in the previous period squared. And I take the square root of that. And that very nicely gives me a development of all the volatilities. So that gives me a nice representation of a return that occurs and the volatility regime that applies to that return. Then on the right-hand side of the fourth table, there you see the fractions of the volatility regime today. So that's the sigma of the asset J at time t plus 1, so which applies from today to tomorrow for the return that applies today to tomorrow, divided by the volatility regime that applies to the return that was observed for asset J over period I. So that exactly is going to be the inflation or deflation factor that we will apply to historically observed returns to make sure that they are appropriate for the current volatility regime that we are in. So if we do that, so then we simply calculate historically for 500 returns. So we determine the returns, but then we inflate or deflate them with the factor that I just mentioned. And then you get portfolio returns, which are not the actual portfolio returns that would have happened in the past, but these are the returns that are volatility regime adjusted. So the return gets this inflation or deflation factor, so and are then made representative. If we do that, and we do that for the 500 past returns, then we get 500 possible portfolio return outcomes for today to tomorrow. So then we translate the historically realized returns adjusted for volatility. We transform them into a probability distribution function for today to tomorrow. Then again, if I'm interested in the tail of the distribution function, I'm going to sort these returns, these volatility regime adjusted returns, from worst to best. The probability of occurrence is that they are all equally likely. So that means that if I look to the 25th worst return, then that's exactly consistent with a cumulative probability of 5%, which means that then the value at risk is that return that we observe there, which is minus 86 basis points. So that's the first element. The expected shortfall follows as the average of the returns, which are even worse than the value at risk. So that's in lines 1 to 24. Take the average of all these numbers, which gives then an expected shortfall return of minus 1.15%. So this historical simulation method and its extension, it's a very nice way to generate value at risk assessments and expected shortfall assessment without making assumptions about probability distribution functions, about co-movement representations and so on. It simply says, well, what you have seen in the past is applicable for the future. And the extensions that we showed made sure that that this homogeneity assumption and also the stationarity assumption for the random dynamics that works. A thing that is important is that, well, we have determined a value at risk and also an expected shortfall, but this was based on historically observed data, and because of the fact that there is a limited number of observations, this value at risk calculation comes with uncertainty, which really means that I report a value at risk, but in fact I am uncertain about the exact value of this value at risk. And the question is, well, could you give a measure of accuracy for the value at risk that you report? And the answer is yes, because really what I'm doing is that I have a distribution function which then has a quantile, and this quantile is in fact the value at risk. And the question is, well, if this distribution function is measured with uncertainty, then also the quantile is measured with uncertainty. And is there a formula to give me a standard error for this quantile? And the answer is yes, of course. Some theory, well, let's more general. Let's denote the quantile that occurs, say with a probability of Q in the left tail. Let's denote that with X, and let's assume that we have determined the probability distribution function from capital T historical returns. And then what we need is the probability density function of that quantile, and that's denoted with a small fx. And for ease sake, in the later application, you could assume that the probability density function simply is a normal distribution function, and then because what you need then to represent the probability density function of a normal distribution function is that you need to know the mean and the standard deviation of all the observations, and then you're done. That obviously is a proxy because the tail of a distribution function, and so then also the quantile, is better represented by other distribution functions. So you could also, instead of using the probability density function of the normal distribution, you could use, for example, a Pareto distribution function. But then the same formula that you will see applies, but only then you need to estimate the probability density function for that other distribution function. So what's the result? The result is that if I look to the standard error of that quantile that I determine, so in our case that quantile will be the value at risk, then the standard error is 1 over the probability density function. In our case, that will be the probability density function of the normal distribution function. And then you take the square root of 1 minus q times q, where q is the certainty that you have that the value at risk will not occur. So in this case, q could, for example, be 90 or 95%. And then there would be probability mass left of 10%, 5% in the tail. That says 1 minus q times q. And you divide it by the number of historical observations. So what does this mean? This means that if I have more historical observations, so then my capital T is higher, then I will be better equipped to determine a value at risk. My value at risk will be more certain because I see that I divide by T, which then also means that my standard error will be lower. Second thing that I see is that the farther I go into the tail, so the higher the Q is, the higher my standard error will become. So for lower Q's, the numerator 1 minus q times q is lower, which also means that my standard error is lower. So we will soon see an example of how to apply this, but so let's translate this more general representation into the value at risk context. So we could say that the quantile that I'm looking at is the value at risk, so then the x is equal to the value at risk. The confidence level q is equal to x, to the probability of certainty. And then once I have determined the value at risk as I did before, then not only should I then report the value at risk, but I could also give a confidence interval for that. And here I assume asymptotic normality, which says, well, take the value at risk that you have determined and subtract 2 times the standard error and add 2 times the standard error. It says 1.96 because that's the exact 2.5% and 97.5% percentile of the normal distribution function. But that gives you an interval where you're 95% certain that the value at risk actually will be. As an example, so I generated 200 possible losses. So the first column gives then the number of the loss. So this table has the first 50 on the most left part of the table, and then the next 50 losses on the right hand side of the table. So we have these possible losses in column 2, and in column 3 they are sorted from biggest loss, so the most worst loss, and then on the right hand side of the table you see the losses which are less extreme. So we see that the worst loss from these 100 is 142, then 138, 136, 133, 132, and so on. So we have 100 observations, that's then the n. We have a certainty level of 90%, and we need the probability distribution function. And to make it easy, we simply said, well, let's use the probability density function of the normal distribution. You see the formula on the right hand side, that's the 1 over the 2 pi times sigma, and the exponent of -1/2 x minus mu over sigma squared. So if I look to this table and I have to determine with 90% accuracy the value at risk, then you look to the 10th element, which is 127, so that would be the value at risk that I report. I also need the parameters for this probability density function of the normal distribution function. So I should take the mean and the standard deviation over all 100 losses, which the mean is 102 and the standard deviation is 19.64. Given that I have the probability density function, given that I have the number of observations, and given that I have the critical value, I can use the formula of the standard error that you see on the previous slide. So I simply fill in the fx, the q, the 1 minus q, and the number of observations, the t, I take the square root. And then I arrive at a standard error of 3.36. So I report a value at risk of 127, a possible loss of 127, a monetary loss. And the standard error is 3.36. Now, how should I interpret 3.36? Well, I could do plus 2 times the standard error, and I could do minus 2 times the standard error, and subtract that hence from the 127, or add it to the 127 to give me a confidence interval. So what I do is I report a value at risk of 127, but I also have to say, well, to be really certain, the confidence interval, so I'm 95% certain that the value at risk is somewhere between 120 and 133 to reflect the accuracy of my value at risk that I report. And you see that there is some real deviation from the number that I report. So it's something to take into account. So let's move to the last part of today's lecture, which is concerned with extreme value theory. Extreme value theory really looks to the tail of the probability distribution function. More specifically, it looks to the right tail of the probability distribution function. So often when we apply extreme value theory, we no longer look to returns, because then we would normally say negative returns, but we look to losses. Monetary losses will be the unit of measurement. And because we talk about losses, the higher the number, the higher the loss, that automatically means that you look to the right tail of the distribution function. The reason why extreme value theory is important is that, in particular, when we do risk management, we already saw that many times we talked about value at risk and expected shortfall. We talk about representations of the tail of the distribution function. How bad can things get? Well, sometimes you're interested in events that could occur with a very low probability of occurrence, that these things that you're interested at are not even in your data. And then it's good to have a representation, a proper representation of the tail of your distribution function. And we discussed that earlier when we introduced the power law. And we're going to revisit that same principle as there was with the power law, but we will look to a more generalized case of it. So the power law is a special case of what we will discuss here, because what we will present here is the generalized Pareto distribution function to reflect the behavior of observations in the tail of a distribution function. So there is a result from Gnedenko, who says, well, if you look to observations very far in the tail of a probability distribution function, and you're only interested in these returns very far in that distribution function, then a good proxy for that right tail is actually to use well, extreme value theory, and then you arrive at the generalized Pareto distribution function. So once more, we look to losses, to monetary losses as the unit of measurement in everything that we do, so that makes it easy to look to the right tail of the distribution function. So some probability theory next. So with capital V, we indicate a random variable which reflects a possible loss. And with the small u, we reflect the start of the tail of the distribution function. So u is the loss. Any loss higher than u will be in the tail of the distribution function. So then if I look to the probability of the loss v being between u and u plus y, conditional upon that the loss is bigger than u, then really what I'm doing is that I'm saying, well, I'm looking to probabilities in the tail of the distribution function because the v is larger than u, that's the condition. And I'm looking then in particular to losses which are somewhere between the start of the tail, u, and an amount y further into the tail. So you arrive at a loss of u plus y. And then this representation of the tail is exactly, and that's the result, the Gnedenko's result, is you can exactly represent that with a generalized Pareto distribution, and that's the second formula. So it has this representation of 1 minus 1 plus xi y over beta to the power 1 to the power minus 1 over xi. So we see that there are two parameters there, the xi and the beta. You can easily estimate them using a maximum likelihood based on observations in the tail. The y is the amount that you are in the tail. So once you have the xi and the beta, you know exactly what the probability is that an event in the tail would occur. Then afterwards, if I move from this conditional probability function, so on the top I look to probabilities that occur under the condition that my loss is in the tail. Well, instead, in reality, I don't know upfront whether I will be in the tail. So simply I'm going to look to a loss v bigger than an amount x. Then I get to an unconditional probability function because I may be in the tail and I may be not. And then, so the translation from this conditional probability function, which is then the generalized Pareto distribution, to the unconditional one, is that I say, well, if loss v exceeds a value x, and I want to know the probability of that, I simply need to take the number of observations that are in the tail, and so all the number of observations that are larger than this value u, and that's where my tail starts, divided by the total number of observations that I have, so both the observations in the tail and the observations that are not in the tail. And then there are these parameters xi and beta reappearing that you should estimate with maximum likelihood from the generalized Pareto distribution. So I get this, this unconditional probability function for the loss. Well, once you have that probability distribution function, it's quite easy to determine expressions for the value at risk and the expected shortfall, because you simply know that the certainty level for the loss should be 99%, so there should be only 1% left in the right-hand tail. So that means that the probability that the loss is larger than x, the probability is larger than the value at risk. So I substitute for x the value at risk, and that probability is then 1 minus q. So if I have that formula then on the top right, I can rewrite it to express the value at risk in that. So that means that I rearrange and I get the value at risk, which is the boxed formula. So there is only parameters in there that you either have determined by maximum likelihood or that you have set yourself. So there is the parameters beta and psi in there, which you have estimated with maximum likelihood. And then there is u, which is where you say that the tail starts. So that's a number that you select yourself. There is the number of observations that you have, that's n. The number of observations that are on the tail, that's nu. And there is the certainty level that you have set, for example, to 99%, the q. And the expected shortfall has also then these parameters, beta and psi, that you've estimated with maximum likelihood. And then there is the value at risk, and there is the amount where the tail starts that you use. So in a way, once you have the beta and the psi, it's easy to determine the value at risk and the expected shortfall. Important, we talk about the right tail of the distribution function because we talk about losses, and this theory only applies to the right tail. So should you have expressions denoted, for example, you have negative returns, then you could always put a minus sign in front of that, which means that you shift from the left tail to the right tail, and then you can apply the theory again. Then the selection of the amount where the tail starts, so the u. So very simply what you could do is you could take the 95% quantile, or you could do as we did before when we did the power law, where we took the logarithms and we said, well, in the tail there should be this linear relationship after you have done the transformations. But the easiest thing is simply to say, well, take the 95% quantile of the empirical distribution, that's where your tail starts. Then an example. So let's start with the parameters psi and beta. So I have the generalized Pareto distribution and its expression, and this generalized Pareto distribution applies to events in the tail. So what I should do is I should use the observations in the tail to fit the maximum likelihood that comes with the generalized Pareto distribution. If you do that, you get parameters psi and beta, in this case 0.371 and 43.526. I know the number of observations that I have. Suppose I have 500 loss observations. And let's assume that I put the threshold of where the tail starts at a loss of 200. And then in the table below, and this table has been sort of made up to make sure that I could fit it on the page. So I have 13 losses that have been sorted. So at loss 200, the tail starts, and all the losses afterwards, 202, 211, 217, all up to 499, are 12 observations which are in the tail, which are my tail observations. So then the number of observations in the tail indeed is then also all the number of observations worse than the observation where the tail starts, just worse than u, so that which is then 12. So now I have my parameters for psi and beta. I have the n and I have the nu. I know where my tail starts, which is the u. So then the only thing that I have left to choose is the certainty level that I want to apply. So suppose that I want to determine my value at risk and expected shortfall with a tail probability of 1%, which means say with 99% certainty. Then I fill in the formulas for the value at risk and the expected shortfall. So I have the U, the B, the Xi, the N, and the NU. So I fill in the Q, and then I get a value at risk of 245. I can then also easily fill in the formula for the expected shortfall, which is 341. Interestingly, what you also can do, because you say, well, now I have defined the behavior in the tail of my distribution function, so I could also go to certainty levels that I could not directly observe in my data, but I go very far in the tail. And for AA and AAA financial institutions, that's important because they look to certainty levels of 99.9%, 99.95%, 99.99%, so very far in the tail. So you could not directly do that with observed data, with observed losses, but you could first fit the observed losses, then get an estimate for the tail using the generalized Pareto distribution, and then extrapolate. And that's what we do at the bottom of this last table. So we take a certainty level of 99.9%. I can very easily fill in the formulas for the value at risk and the expected shortfall. So the loss here is then 464, and the expected shortfall is 800. And so I am very far in the tail if I do that, because there's only one observation that was worse than the reported value at risk, which is the worst observation that we had. And this concludes the presentation of the lecture of this chapter. Thank you for your attention.